So today we'll be doing an advanced Turing reduction. These reductions are usually considered advanced because they usually involve creating a machine within a machine, which is always weird to understand at first, as it was for me. And so my hope with this video is to make it a bit more intuitive as to why we're making a machine and kind of how to make that machine in the first place, like that inner machine we're talking about. So the language that we're trying to prove is undecidable is L finite. So L finite, it takes in a machine and we accept that machine if and only if the language that that machine decides is finite. So the language of this machine, the language that it decides is finite. So let's do some examples. We want to prove that it's undecidable, but before we prove it's undecidable, let's go through some examples as to what would be accepted into this language or what would be as an element in this language and what would not be an element in this language. So for example, the machine of the empty set. This would be this would be an element of our language because if it's the empty set, it actually rejects everything. So the language of this machine is just empty. And because it's empty, it has zero elements is finite, therefore this machine would be accepted into our language or be into our language. Another example could be m oh my gosh. M each 376 each it will say each classes. So this machine accepts all strings of all the different each class at U of M. So we could have something like 183, 203, 376, etc. This will be finite because we only have a limited number of each classes at the University of Michigan, sadly. And so this is this is also a finite language, and therefore this machine would be in our L finite language. And one thing that wouldn't be accepted or wouldn't be part of our language would be the language of odd numbers, because then this set would be it would accept the here, let me be a bit more clear about this. The language of this machine, the language of this machine is that set. The language of this machine would be all the odd numbers in the world, which is infinite. So we would have something along the lines of 1, 3, 5, 7, dot, 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 dot. This is infinite because it is not finite. It would be rejected, or the machine would be rejected. And so this is just some examples of what would be part of our language and what would not be part of language. And the goal of this is to prove that L finite is undecidable. One of the best ways to prove that language is undecidable is by a Turing reduction, as we've learned in class. And so in a Turing reduction, we would usually, because we want to prove that it's undecidable, what the best approach is to put L finite in place of B. Because if we can find an undecidable language and put it in place of A and show that basically some undecidable language is Turing reducible to L finite, we will then prove that L finite is indeed undecidable. And so in terms of choosing your undecidable language, you can choose whichever one you want unless we specified otherwise on a homework problem or an exam. So if we say, hey, you must use L accept, you must use L halt, you must use whatever, you have to use that. If we don't, if we just say prove it's undecidable, you can usually just choose whichever undecidable language you want. I most prefer L halt, just because I'm most comfortable with it. So what I'm going to show you in this video is a reduction is show that L halt is Turing reducible to L finite. And by doing this, I will then prove that L finite is undecidable. So in terms of how we approach a Turing reduction, remember there are two parts to it, right? There are two parts. First thing we do is assume we have some decider for L finite. So I'm going to call that M finite. Actually, I'll call that just F for clarity. Assume we have F. F is a decider for L finite. All right. And the second thing we have to do, this is our Turing reduction steps. Second thing we have to do is then create a decider for L halt. So we'll do that. We'll call that M halt. So that is the steps we have to do in this Turing reduction. First, assume we have a decider for L finite, which we will call F. Then create one for L halt. We'll call that M halt. So this is what we have to do for our Turing reduction. Now that we have thought about what we have to do in terms of Turing reduction, let's actually start implementing the reduction. And so let's start by creating M halt. I'll use a different color for this. We know that M halt, or just the halting problem in general, it takes in inputs M and X. It should, and this is just for our understanding, it should accept if M halts on X and reject if M loops on X. So this is what we have to make. Let's go ahead and start making it. So we have our decider, M halts. It takes in a machine and X, and we want to implement that following. Now, when you reach this point, my suggestion, stop. Don't start creating the machine right now. What I suggest otherwise is start off with correctness proof. Because when you create the correctness proof is essentially a blueprint for how your decider actually works. So if you create the blueprint first, now it's much easier to actually create the machine. And so what I like to do is always start off with the actual correctness proof. And even we start off with at the end of the correctness proof, and then we build towards the beginning. But when you reach this point, stop. Let's actually work on the correctness proof first before we work on the actual machine, because I think it's much easier, much better to understand, and much easier to create the actual machine itself. Now, in terms of the correctness proof, let's think about how correctness proof usually starts off. So what we have is usually we have M halts on X. In the case that M halts on X, we have some transitions, and then eventually we have that M halts accepts M and X. If M halts on X, we want it to accept. So this is usually how it goes. And the same thing, that M loops on X, we have something, and that M halts rejects M and X. So let's remember that for these correctness proof, we usually use the black box decider that we assumed. So they look like, even more descriptively, they look like, I think that's a word, descriptively, I hope. So they look like something like, okay, F accepted something, which led to this, and F rejected something, which looked like this. And that's what our correctness proof looks like. The thing is, though, we just constructed this relationship between F and M halt. Like, it's not actually that we don't know if it's going to be the case that when F accepts whatever input we give it, M halt accepts. We just decided that right now. And so what I suggest as the first step is you create this relationship right away. You decide whether if you want F accept whatever we give it to lead to M halt accepting. And if F reject whatever we give it, M halt reject. You should decide this first before you even create your machine. Now you may say, Yusuf, I don't even know what we're passing to F. How would I know if it's going to accept or reject? Well, you don't. What I'm saying is just choose a relationship. Make it accept, or reject, or choose the opposite. Accept, reject, accept. Choose either of the two options. If it turns out to be correct in the end, perfect. It worked out. If it doesn't, well, we can make that adjustment along the way. But choosing this relationship first can really make it easier for you to see how we create the machine, how we create this decider, and how we create that inner machine. It makes it much easier to do so. So my first suggestion, the first step, choose this relationship, whether it should be accept, reject, or the opposite, the yes, no, no, yes. So that's your first step. Choose this relationship. Now you may ask Yusuf, okay, we've created this relationship, but what do we even pass in to F? Well, in other reductions that we've done, we usually just pass in the same variables that were given to our decider. So usually what we would do in our decider, we would do something like run f on m and x. The problem is we can't do that because our decider only takes in one input. So we can't just pass in m and x because it only takes in one input. We can't pass in two. So what do we have to do? Well, remember the goal of what we care about is, does m halt on x? So what we want to do is somehow encode the results of m on x into one singular input. We're encode the result of m on x into one singular input. How do we do that? Well, we can do this by creating a machine. So if instead of running f on m on x, what we do is we construct a machine m prime that we can hard code m on x into this machine, and we can say, hey, run m on x. Run m on x. And we can do this. This is legitimate in both ways. This will not loop. Create a machine will not loop. We've learned how we can do that, and it's perfectly fine. And we have access to m on x because of what's above. We can always hard code the results into our machine. And now we have that ability. And so now when we do something along the sorts of run f on m prime, we're basically running f on the results of m on x, which is perfect, which is absolutely perfect. F can start calculating m on x instead of just passing in. Instead of doing this, which is incorrect, we can just pass in m prime, which is going to include the results of m on x. So now we've transformed these two inputs into one, and now we can actually use the black box decider that we've always wanted to use, and that can really help us make this a case where it's possible to loop on for m and loop on x. Now it may not ever loop because of how we're structuring this. Cool. So now we've realized that the input we want to make for f is m prime. Let's now add that into our correctness proof. So let's make it a little nicer. We say, okay, m halts on x. And then we have something something happens here. We have now that f accepts m prime, because remember how we talked about I chose for just do accept because I wanted to start off that way. It might be wrong, it might be right, we don't know, but we're constructing that way initially. F accepts m prime, and therefore m halt accepts m on x. And then also likewise, m loops on x. Something happens, f rejects m prime. Therefore, m halts rejects m on x. So let's add that last part to our machine. We say, okay, if it rejects, if f accepts m prime, accepts m and x, else rejects m and x. So now this machine is mimicking this correctness proof that we're creating initially. So now we have this. Well, in the case that m halts on x, let's think about how we actually want to create m prime now. In the case that m halts on x, we want our f to accept m prime. Well, when would f accept m prime? Well, f accepts m prime if the language of m prime is finite. So how about in the case that m halts on x, we just make the language of m prime finite. So we say in our machine, okay, if it halts, in this case, that could be accept or reject. We want to make the language of m prime finite. Well, how can we do that? We can choose, what if we just chose one of the languages we talked about before? What if we just chose the empty set? And the empty set, the only thing we have to do is reject every input, and we know that's finite. So how about we say if m halts on x, m prime just rejects everything. And also one thing I forgot to include, m prime takes an input w. We can just ignore that input. We don't have to do anything with it. You don't have to do anything with it. We can just say, hey, run M on X. If our if M halts on X, we just reject W, which means we reject every single possible thing. And therefore, the language of M prime, if we reject W, language of M prime is the empty set. That's finite. So in this particular case right here, we constructed our machine such that when M halts on X, the language of M prime, language of M prime is finite, which is perfect. Because then F will accept M prime, and then M halt will accept M on X, which is great. And what we want for the looping part is we want F to reject M prime. In order for it to be rejected, the language of M prime has to be infinite. So that's what we want right here. We want the language of M prime to be infinite. Now let's make sure that that works in our machine. So we said, okay, if it halts, we reject everything. Else, if it loops, we want to choose some infinite language, something that'll make L of M prime infinite. Well, if we just accepted everything, then we accept all inputs, which is infinite. So we can do that. And now we've created our machine. It works. It goes our correctness proof. Our correctness proof works. It goes exactly what we want. And now we've created a machine for M halt. So we're done. Except we're not. Because there's one small error. And this is the thing that I talked about in the beginning where we might assume this relationship between F and M, but it may not initially work. And so why doesn't it work? Well, if M halts on X, it works. It's perfect. Because when M halts on X, if this is line 1, line 2, line 3, if M halts on X, it'll then go to line 2, it'll then reject W, and it'll be done. So when M halts on X, it's great. But what if M loops on X? Well, if M loops on X, it'll never actually leave line 1. It'll just be stuck on line 1 forever. It'll never go down to line 2 or line 3. In the case that it just sticks on line 1, it never accepts anything because it never escapes line 1. If it never accepts anything, then the language of M prime is just nothing because it doesn't accept anything. And so in this case, we wanted L prime to be infinite, but because it doesn't accept anything in the case that M loops on X, it turns out it's just finite. So it's incorrect. And so now what do we do? Does our whole world break down because our initial relationship was incorrect? No. We can just switch our relationship. What if because M looping on X guarantees that the language of M prime is going to be finite, what if we just switched it? And instead of making instead of making it infinite for this case, we just make it finite instead. And in this case, instead of making it finite, we make it infinite. We'd also have to switch it for the reject. So then if the language of M prime is infinite, F would reject M prime. And in this case, it should accept M prime. Does this still work? Well, if M halts on X and we created it such that L of M prime is infinite, then F would reject M prime, which is great, which is fine. That would work. And then M halts would accept. So we'd have to change our machine such that if F accepts M prime, we want our M halt to reject. There's no problem with that. We're literally creating our machine. We can make it whatever we want. So we just change it to be like that. And if F actually rejects M prime, we want our M halt to accept. So accept M on X. So we've created this. We realized that our initial assumption of accept, and reject was incorrect. So what we did, we just switched it. We now made it such that it should be a reject to then an accept and an accept to then reject. Because we realize that's actually going to work now. Because this guarantees when M loops on X, M prime is guaranteed to be finite. So then in this case, we need to make it such that we need to make that part's already taken care of. So now what we have to do is make sure that in this case, it's infinite for the case that M halts on X. So when we go to M prime, initially we rejected everything. But what if we just wanted, we can just say, hey, accept W. Now that makes it infinite. And we'll never even reach line 3. So we can just take that out of the way. That's just incorrect. And so now we've created our machine. We realized that when we did accept, and reject, it was incorrect. But instead of us just destroying the world and everything goes wrong in the world, we didn't need to like nothing went wrong. All we had to do was just modify or switch our initial assumption. Instead of being accept, accept, and reject, reject, we made it to be accept, reject, and reject, accept. And by doing so, we had to modify a couple things. We had to modify, okay, when we run M on X, we want to make it such that if it halts, we want to make our thing infinite to adjust for this new thing that we created. To make it infinite, okay, we just accepted everything. That's just one way of creating infinite language. You could have said accept W only if it's odd, accept W only if it's even, because those are also infinite languages, whatever. So we chose to make our M prime infinite. And when M loops on X, we know automatically that it's finite. And so then we say, okay, run F on M prime. If F accepts M prime, then reject it based off our correctness proof. And if it rejects M prime, then accept it based off our correctness proof. And our correctness proof works alongside our machine. And so this is the strategy that, and now we've created a Turing reduction for M halts. So we've now shown for L halts. So now we've shown that L halts is Turing reducible to L finite. And we have our machine, we have our correctness proof that works. And now we've created our Turing reduction. And now we've proven that L finite is undecidable. Now, again, what I really want to emphasize in this situation is don't get started on the machine right away. The first step that you should do is create a relationship between your black box decider and the one you're trying to create. So we'll say the decider you're creating. Then you figure out how to make M prime such that it would fit, just as we did. We realized we wanted to make it a linear to M prime finite or infinite based off whatever happened with M on X. It would work. Check. We needed to check to make sure that it works for both cases. For both cases, we realized it didn't, so we had to just switch the inputs. So if it doesn't, inverse relationship and modify. And then once we inversed our relationship, we had to modify machine and correctness proof. Once we did that, we make sure that everything works out. And once we did that, it worked. It worked out. And so again, create the correctness proof first. That's my main takeaway. This create the correctness proof first. Figure out how you make your M prime. Then that way it'll make it much, much easier to actually create the machine itself. And so yeah, that is my main takeaway for this video. That's what I hope that you get out of this video is create the correctness proof first, then the machine, then becomes much easier. Make sure to check that it works for both cases. That's the most important part. If it works for both cases, then you're set. And so, yeah, if you have any questions, please let me know. If there's any errors or any confusion with the videos, please let me know. And then I can always make a post on Piazza or make another video if necessary. So we have a great rest of your day. And thank you so much.